Hey everyone, thanks for inviting me. This talk is about fair allocation of indivisible goods. I'm Eklavya. I'm a PhD student at UIUC, advised by Professor Jugal Garg. Okay, so today I'll first introduce what the problem is, the problem of fair allocation, also known as fair division. And then I'll talk about two of my recent results. The first is new fairness concepts for allocating indivisible items. And this is joint work with Ioannis Karagiannis, Jugal Garg, Nidhi Rathi, and Giovanna Varicchio. And the second result, which I'll only talk briefly about, is simplification and improvements of MMS approximation. This is joint work with Hanane Akrami, my advisor Jugal Garg, and Satare Taki. So in the fair allocation problem, we are given a lot of goods that we want to distribute among n people, also called agents. And these agents are equally deserving. So we don't want to discriminate against any one of them by giving some agents too much and the other agents too little. Okay, this is roughly what we mean by fair. Okay, so let's now try to formalize the problem. We are given a set capital N of agents where the number of agents is n, and we have a set M of goods where the number of goods is little n. And for every subset of goods and for every agent I, we define Vi of S to be a number that tells us how much does agent I like the set S of goods. Okay. Here, Vi is called agent I's valuation function. So in this talk, I'll assume that Vi is an additive function for each I, which means that Vi of a set of goods is equal to the sum of the values of the goods in that set. And for simplicity, we define the value of a good to be the value of the singleton set containing that good. Yeah, okay. So an allocation X is a specification of which agent gets what goods. So we formalize this as an n tuple where the ith entry xi is the set of goods that agent I is supposed to get, and xi is called agent I's bundle in allocation X. Our aim is that we want to find an allocation that is fair. Okay, so what exactly do we mean by fair? There are many different notions of fairness. Okay. So before I get into the notions, let me first build some intuition by considering a simple example. Suppose there are m identical goods and there are n agents. Then intuitively, it seems like the most fair way of allocating the goods is that each agent gets either ceiling of m by n goods or floor of m by n goods. Okay. So how do we generalize this idea? So there are two key observations there, and each observation gives us an approach to fairness. The first observation is that if you look at any two bundles, they differ by at most one good. And this gives us what we call an envy-based approach, that if we want any two bundles in an allocation to not be too far apart from each other. Okay. And the second observation is that each agent gets roughly 1 over n fraction of goods. Okay. This is called the proportionality-based approach, which means that each agent gets roughly 1/n of the entire set of goods. So let's first focus on the envy-based approach. In an allocation X, we say that agent I envies agent J if agent I's value for her own bundle is less than the value she has for agent J's bundle. And we say that agent I strongly envies agent J if there is a good in agent J's bundle such that even after removing that good, agent I still thinks that her bundle is worse than agent J's bundle. So we say that an allocation X is envy-free if no one envies anyone else in the allocation X. And we say that X is envy-free up to any good, abbreviated as EFX, if no one strongly envies anyone else. So let's look at an example here. On the left, I have a table that has two agents, Alice and Bob, and we have 4 goods. Suppose we give the first 2 goods to Alice and the last 2 goods to Bob. Okay. And on the right-hand side, I've drawn a table that tells us what value each agent has for each of the bundles in such an allocation. So here we see that Bob's value for his own bundle is 29 and his value for Alice's bundle is 28. So Bob does not envy Alice, but Alice envies Bob because her value for her own bundle is 8 and her value for Bob's bundle is 9. So this is not an envy-free allocation. But we can see that this is an EFX allocation because as soon as we remove any good from Bob's bundle, then Bob's bundle would have a value of at most 7 to Alice. And then Alice would, so Alice does not strongly envy Bob, and so this allocation is EFX. So it's quite easy to see that envy-free allocations may not always exist. For example, if there is a single good and 2 agents, then whoever we give the good to will be happy and the other agent would be envious. So, but what about EFX allocations? So we have 2 important problems there. The first is that do EFX allocations always exist? And can we efficiently compute EFX allocations? So this has been an open problem since 2016. And we know the answer for some special cases, like if all the agents have identical valuations, or if there are only 3 agents, then EFX allocations always exist. Okay. But in general, it's not known if they exist or not. For this reason, many relaxations of EFX have been studied. For instance, EF1, alpha EFX, and EFX with charity.
So can I ask a question?
Yeah, sure.
So maybe these are covered in these relaxations that you mentioned, but is there a constant C such that there always exist envy-free allocations if we remove up to C items? Is that so? EFX is C equal to 1. Is that true? But maybe that's not true because there could. Yeah, I'm just wondering: is there some such relaxation? That may be a reasonable conjecture to make.
Yeah, I think those relaxations have been studied. So these are like EF2 and I think they're called EFKX, but I'm not aware of what the current results are for those.
But people there is a general belief that EFX may be true.
I don't know. I think different people have different conjectures, so it's not like not like P not equals NP where like almost everyone believes that it's not true. And for EFX, it's like mixed.
I see. And also envy-free allocations are, of course, a classical area. When were these formulated like EFX? Maybe more recently, the last 25 years or so?
Yeah, I think EFX was given in a paper by Karagiannis in, I think, 2015 or something.
I see. Okay, thank you.
Okay, so this was about the envy-based approach. Now let's look at the proportionality-based approach. Okay. We say that an allocation X is proportional if for every agent I's value for her own bundle is greater than or equal to her value for the entire set of goods divided by n. Here this value Vi of m divided by n is called agent I's proportional share. And so an allocation is proportional if every agent gets a bundle of value at least their proportional share. Now again, proportional allocations may not exist. If there's a single good and there are 2 agents, then some agent will get nothing. So the next question we look at is, can we get a better notion of fairness by using some other threshold for each agent other than the proportional share? Okay. So let's consider this example again. We have 10 identical goods and 4 agents. Then no matter how we divide the goods, some agent will get at most 2 goods. Okay. And in this allocation that I've shown here, every agent does get at least 2 goods. So it looks like a threshold of 2 would make more sense here instead of the proportional share, which would be 2.5. So how do we generalize this idea? We generalize this using a notion called maximin share. Okay? So let capital pi be the set of all partitions of the goods into n bundles. Okay? And we define agent I's maximin share, also known as the MMS value, by this expression here. Okay? And we say that an allocation is MMS if every agent gets their maximum share. Okay? So now if you've seen MMS before, then this expression would make sense, but some of you may be wondering that what is this complicated expression and why should this be considered fair? Okay. So let me try to explain that. But even if I could explain this to you, let's say if we that everyone, so there are sometimes even lay people may need to do fair division, and then let's say such people go to their local fair division expert and the expert tells them, okay, this is the notion of fairness I'm using. They'll be like, okay, what is this complicated thing. We don't understand this. Okay? So let's see how we could explain fairness to like such people. Okay. So let's say I tell the agents that, okay, instead of me imposing a notion of fairness on you, I give you the freedom that you come up with a partition of goods into n bundles in a way that you think is fair. And then what I would promise you is that I'll give you a set of goods whose value is at least as much as some bundle in the partition that you proposed. Okay? So formally, agent I would propose a partition Z, and then we'll promise them a value of at least the value of the minimum valued bundle in that partition. Okay. And so if the agents are smart, they would know that since this is the guarantee that we're giving them, they would want to maximize this guarantee. And that's why they'll pick an allocation that maximizes the value of the minimum valued bundle. Yeah, so this is what we mean by maximin share. Okay. So again, MMS had been a compelling fairness notion, but in 2014, it was shown that such allocations need not exist. So there are some, so when all agents have identical valuations, then MMS allocations exist. But in general, there's a very non-trivial example that shows that such an MMS allocation need not exist, even if there are only 3 agents. Okay, so far, this is the situation that we looked at EFX and MMS, which seem to be very good notions of fairness, but we've seen that EFX has been a very hard problem that's been open for a long time, and we know that MMS doesn't exist. So what do we do now? Okay, so we need to look for slightly weaker notions of fairness, along with guarantees of their existence and the ability to compute such allocations. Okay. So in this talk, I will talk about 2 notions of fairness. The first is epistemic EFX, and the second is approximate MMS. Okay, so since it's not possible to guarantee every agent their maximum share, can we at least guarantee them a large fraction of their maximum share? Okay? So for some constant alpha between 0 and 1, we say that an allocation X is alpha MMS if each agent gets at least alpha times their maximum share. And we want to find the largest alpha for which maximum share, largest alpha for which alpha MMS allocations always exist. Okay, so now I go on to part 1, which is about epistemic EFX. Let's start with an example here. Suppose we have 3 agents, Alice, Bob, and Charlie, and we have 9 goods. Okay. Now, assume that all goods are identical to Alice, but these goods may not be identical to the other agents. So consider allocation A, where each agent gets 3 goods. Then in this allocation, Alice does not envy anyone. Now suppose Bob and Charlie decide to swap some goods among themselves. Now once they do that, we get allocation B. And in this allocation, we see that Alice strongly envies Charlie. So here we have a strange situation where in both the allocations, Alice has the same set of goods, but still she considers allocation A to be fair and allocation B to be unfair, if we go by EFX as the notion of fairness. Okay. So this brings us to what I call the mind your own business principle. So this says that whether an allocation is fair to you should depend only on your own bundle and the fair division instance. Whether an allocation is fair or not should not depend on how the remaining goods are distributed among the other agents. So we see that proportionality and maximum share follow the mind your own business principle, because whether an allocation is fair or not, it only depends on whether an agent's bundle has at least a certain threshold value or not. Okay. Whereas envy-freeness and EFX don't satisfy this principle. Okay. But violating this principle doesn't mean that the notion of fairness is bad. It just means that it's too demanding. For instance, EFX tells us that not only is an agent getting a sufficiently large set of goods, but it also says that every agent thinks that the set of goods that that agent is not getting, those are distributed roughly evenly among the remaining agents. Okay. Also, EFX allocations may be unstable in some sense. Like it could happen that we somehow compute an EFX allocation, but some agents, but after this allocation has been proposed, some agents swap some of the goods among themselves, and then the resulting allocation may not be EFX. Okay? And in general, it could be very hard to enforce agents to not swap goods among themselves, because once the allocation is done and the agents go home, then we can't really control what the agents do. So this brings us to the notion of epistemic fairness. We say that an allocation X is epistemic EFX if for each agent I, we can redistribute the goods that goods outside agent I's bundle among the remaining agents such that I does not strongly envy anyone anymore. Okay. So formally, we say that an allocation X is epistemic EFX if for each agent I, there is another allocation Y such that agent I gets the same set of goods in both X and Y, and agent I does not strongly envy anyone in the allocation Y. Here, Y is called agent I's certificate of fairness. And in an epistemic EFX allocation, different agents can have different certificates. So let me take an example. So if you look at this allocation on the left, allocation X, this is not an EFX allocation because Alice strongly envies Charlie. Okay. But this is an epistemic EFX allocation for Alice because there is another allocation Y where Alice gets exactly the same set of goods, and in Y, Alice does not strongly envy anyone. Okay. So epistemic EFX follows the mind your own business principle. And although it's a relaxation of EFX, at least I believe that it's almost as good as EFX. Okay. So a natural question then is that do epistemic EFX allocations always exist? And we answer that yes, they do exist. And in fact, we can efficiently compute them also. Yeah. So in 2017, Burman and Krishnamurthy gave a polynomial time algorithm to compute 2x3 MMS allocations. And we show that their algorithm's output is also epistemic EFX. Furthermore, we also show how to extend their algorithm to output the certificates for all the agents. So not only is the allocation fair, the agents can also verify that the allocation is indeed fair. In our paper, we also define another notion of fairness called MXS, which is a threshold-based notion of fairness. So it's basically the minimum value that an agent I's MXS threshold is the minimum value that agent I gets among all allocations where she does not strongly envy anyone. So we show that any MMS allocation is also an epistemic EFX allocation. We show that any epistemic EFX allocation is an MXS allocation, and then any MXS allocation is a prop 1 allocation. So prop 1 is a notion of fairness that I haven't talked about yet. Also, we show that epistemic EFX allocations are 4/7 MMS, and this almost follows from a previous result. And this previous result says that EFX allocations are 4/7 MMS. So these are the results that we have. Now I'll talk about the algorithm that we use to get epistemic EFX allocations. Okay. So for me to do that, I'll have to introduce a concept called ordered instances. We say that a fair division instance is ordered if in that fair division instance, everyone's favorite item is the same, everyone's second favorite item is the same, and so on. And for ordered instances, EFX allocations always exist and they can be computed efficiently. This was shown by Burman and Krishnamurthy in 2017. Okay. So now we get this idea that can we somehow reduce the fair division problem to ordered instances and somehow use this algorithm for EFX allocations in ordered instances to somehow get epistemic EFX allocations. Okay. So let's first look at the reduction algorithm. So we are given an input I, which is a fair division instance, and we use that to create another instance called I hat. So let's look at this example. We have 3 agents and 5 goods. And to create this instance I hat, we basically take each row and we sort the values in decreasing order. Okay, so 3, 2, 10, 11, 1 becomes 11, 10, 3, 2, 1. Okay, so basically we construct M new goods and we call this set M hat, where agent I's value for GJ is equal to agent I's value for the jth best good in the original instance. The next step is that we find an EFX allocation of I hat. Okay. So as you can see that this allocation would be ordered because since these values are sorted. Yeah. Okay. So the next step is that we find an EFX allocation of I hat. So here, if we look at this allocation, this is EFX. I mean, this is simple to verify, but I won't go through the calculations to show that it's EFX. So yeah, for now, just believe that this is EFX. Okay. The next step is that we create a list, capital A of agents, which we call the picking sequence. And this list can have duplicates. Okay. In this list, the jth element of the list is the owner of the good gj. Okay. So for instance, Alice gets G1, so the first element of the list is Alice. G2 goes to Bob, so Bob is the second element, and the next three goods go to Charlie, so the next three elements in the list are all Charlie. And finally, we just call agents from this picking sequence one by one, and we ask them to pick their favorite remaining good in the original fair division instance. Okay. So let's look at this, our original fair division instance. So here first Alice gets to pick her favorite good. So she picks this bar of chocolate. Then Bob gets to pick his favorite good. He picks this lollipop. And then finally Charlie gets to pick his favorite remaining good 3 times. So far the chocolate and the lollipop have already been taken away by Alice and Bob respectively. So only these 3 goods are left. And Charlie just picks all 3 of them. And this gives us our final allocation. Okay. So to summarize, we have an instance I as input. We first construct an ordered an instance I hat, which is an ordered instance. We find an allocation X hat of the instance I hat, which such that X hat is EFX. And then we create a picking sequence based on X hat. And then we call agents in the picking sequence, and we allow them to pick their favorite remaining good. So let X be the resulting allocation of the original fair division instance. Okay. So the first theorem that we have is that if X hat is EFX, then X is an epistemic EFX allocation. Okay, so this is something that we prove in our work, and there's another known result which says that for any alpha, if X hat is an alpha MMS allocation, then X is also an alpha MMS allocation. So this basically, so theorem 2 is already known, and this tells us that if we want to compute alpha MMS allocations, then we can assume without loss of generality that the instance that we can assume without loss of generality that the instance is ordered. Okay. So far, does anyone have any questions? Okay, then I'll proceed. Okay, so now I'll try to give you an idea of the proof of theorem 1. So, okay. So suppose in this allocation, suppose when we run this allocation algorithm, agent I gets goods G5, G10, and G13 in the allocation X hat. Okay. So this means that agent I appears at positions 5, 10, and 13 in the picking sequence. So suppose agent I gets the goods A, B, and C in the original instance when agent I gets to pick their favorite remaining goods. Then we can show that agent I's value for A is at least the value of G5. Agent I's value for B is at least his value for G10, and agent I's value for C is at least as much as his value for G13. So would anyone in the audience like to have any idea for why this may be true? I mean, okay, I'll tell why this is true. Yeah. So agent I picks their So in the part of the algorithm where agents pick their favorite remaining good, agent I first gets to pick in the 5th round. Okay, so it means that 4 rounds have already taken place before agent I gets to pick, which means that 4 items have already been taken away by the other agents. So if we look at the top 5 goods of agent I, then out of those, at most 4 have been taken away. So agent I will always get a good from the top 5 goods if they pick in the 5th round. And by the way that we've constructed the ordered instance, the value of G5 is equal to agent I's 5th favorite good. And for this reason, VI of A will be greater than or equal to VI of G5. Okay. And by a similar logic, we can show that VI of B is at least this much and VI of C is at least G13. Okay. So now let's try to formalize this argument. For sets S and T of goods, where S and T have the same cardinality, we say that S dominates T if for every J, agent I's jth best good in S is at least as good as agent I's jth best good in T. Okay. So lemma 1 tells us that the bundle that agent I gets in the allocation X, which is the allocation of the original instance, dominates the bundle X hat I. So, okay, now let's look at what happens to the goods that agent I does not get. Okay, let X of minus I be all the goods that agent I did not get. So it's basically the union of the bundles of all the other agents in the allocation X. And similarly, X hat minus I is all the goods that agent I didn't get in the allocation X hat. Okay. So since Xi dominates X hat I, we get that the total value of Xi is greater than the total value of X hat I. And then we subtract these two values from the value of the entire set of goods. So this tells us that value of X minus I is at most the value of X hat minus I. Okay. So this means that when we go from the ordered instance to the original instance, the total value of the remaining goods reduces according to agent I. Okay. But we can actually show something stronger. We can show that if you look at all the goods that agent I did not get, then when we go from the ordered instance to the original instance, every good becomes worse in some sense. Okay. So let's try to see why this could be true. Okay. So let's take an example where we have 5 goods of values 50, 40, 30, 20, and 10. Okay. And let's suppose that in X hat I, the goods have values 40, 30, and 10, and in Xi, the goods have values 50, 40, and 20. Okay. So this is X hat I, and this is Xi. Okay. Now we'll try to convert X hat I to Xi in an iterative way that will yeah, okay, so let me just show this directly. Okay, we start with X hat I, and then we replace the first good in X hat I by the agent I's favorite good in Xi. Okay. So 40 gets replaced by 50. Okay. Then we look at this set and we replace the second best good by the second best good in Xi. Okay. So 30 gets replaced by 40. And then in this set, we replace the third best good by the third best good in Xi, and so on we go. So this gives us a sequence of subsets of goods. Okay. Now here we see that in each iteration, some good gets replaced by a better good, but at the same time, some good in the complement of that set gets replaced by a worse good. So this means that over time, when we go from X hat I to Xi, I mean, every good, like the goods in the complement would get worse over time. And this tells us that X hat I dominates Xi. Sorry, X hat minus I dominates X minus I. And this completes the proof of lemma 1b. I mean, this is just a proof sketch. Okay. So far, what have we shown? We've shown that when we go from the ordered instance to the original instance, agent I's own bundle gets better, and the set of goods that agent I did not get worse. Now we have a mapping pi from the set of goods in the ordered instance to set of goods in the original instance, such that this mapping maps each good in x hat I to a better good in xi, and maps each good in x hat minus I to a worse good in x minus I. Okay. Now for a set S, let me define the mapping of the set to be the set of all the goods that we get by applying the mapping to each good in that set. So now, since x hat is an EFX allocation, this is what we get by the definition of EFX, that the value of agent I's own bundle in x hat is greater than or equal to her value for agent J's bundle after we remove some good, and we remove a good in such a way that this bundle has we want this to be true for all G. That's why we have a max. And so this basically follows from the definition of EFX. Okay. Now imagine what would happen if I apply the mapping pi to each bundle in x hat. Okay. So if we do that, then first of all, x hat I is mapped to a better good. Every good in x hat I is mapped to a better good in xi, which means that if we apply the mapping pi to x hat I, it will just give us the entire set xi. Okay, because these two sets have the same cardinality. So yeah, so okay, so let Y be the allocation that we get, where the jth bundle in Y is obtained by applying the mapping pi to the jth bundle in x hat. So if we do that, this term on the left will get better. Okay. And this term on the right will get worse because of 0.2 here. So what we get that if we replace x hat by Y, this inequality will continue to hold, which means that in the allocation Y, agent I does not strongly envy anyone. Okay? And furthermore, in allocation Y, agent I gets the same bundle as they get in allocation X. And so this tells us that Y is agent I's epistemic EFX certificate for X. And this completes the proof uh, that the allocation X is an epistemic EFX allocation and Y is the corresponding certificate. Right? So this is all I had to talk about epistemic EFX. And a few open problems remain in this area. That we've only talked about additive valuations, but it's not clear if we can get epistemic EFX allocations for non-additive valuations. There's also we can also try to get other notions of fairness in conjunction with epistemic EFX. So we've shown that we can already get epistemic EFX plus 2/3 MMS, because Burman and Krishnamurthy showed in their paper that the same algorithm gives us 2/3 MMS. But can we get better than 2/3 MMS? This is a problem that I worked on for some time, but couldn't get any results here. And there are other notions of fairness that we can consider, like EF1 and approximate EFX. Okay. Also, in this talk, I only focus on fairness, but in fair division, there is another thing that people care about, which is efficiency, and that is captured using a notion called Pareto optimality. So again, it's not clear if we can get Pareto optimality along with epistemic EFX. Yeah. So does anyone have any questions about epistemic EFX? Okay, I'll go fill my water bottle till then you think of questions. me see. Okay, I'll move to the second part of the talk, which is about approximate MMS allocations. So I'll only briefly cover this. I'll just give a gist of the problem. So let's recall, we've seen that agent I is maximin share value is given by this expression here. Okay? And we say that an allocation X is alpha MMS if agent I's value for her own bundle is greater than alpha times her maximin share for every agent I. So these are the known results that we have for approximate MMS. So first of all, the algorithm by Burman and Krishnamurti, which also gives us an epistemic EFX allocation. This gives us 2/3 MMS. In fact, it gives us slightly more than that. It's 2/3 plus some factor that depends on n. Yeah. In 2018, it was shown that 3/4 MMS allocations always exist, and this is a result by Ghodsi, Hajiaghai, Seddigan, and Young. And then in 2020, this result was slightly improved to 3/4 plus 1/12 n MMS. Okay. But yeah, so far, the algorithms for 3/4 MMS were very complicated and they had a very complicated analysis. So in our work, we considerably simplify the analysis, and then we also slightly improve the factor. Like instead of 1/12 n, we get roughly 3/16. And finally, very recently, Akrami and my advisor, Professor Jugalgar, they showed that 3/4 plus 3/3836 MMS allocations exist. So this is a tiny number, but still it's an important result because it's a constant more than 3/4. And on the hardness side, we know that it's impossible to get more than 1 minus n to the power minus 4 MMS. So there's a huge gap here, even now. Yeah, so as I said, we gave a very simple algorithm for this problem with a simple analysis. And our algorithm is similar to the previous Gargantaki's algorithm, but yeah, our way of analysis is quite different. We also give a hard example for both our algorithm and the Gargantaki algorithm. So specifically, we come up with an input, like a fair division instance I, such that for both our algorithm and the Gargantaki's algorithm, the algorithm's output on this instance I is not better than 3/4 plus 3/8n minus 4 MMS. So in this sense, this hard example was quite useful because before this example, it was not known whether this approach that's being used in these kind of algorithms, whether this approach can give us something significantly more than 3/4 MMS. And using this hard example, we showed that this approach has its limits. Okay? And then by studying this hard example and working around it, Akrami and Garg were able to improve the MMS factor to a constant more than 3/4. Let's see. So I'm not sure how much more time I have left. It's around 15 minutes.
Yeah, 15 minutes.
Okay, so I think what I have remaining would take more than 15 minutes. So I think now would be a good time to end the presentation. If you have any questions, then let me know.
So what are some, longer term and, medium term big questions you can think about in this broad area?
I think one of the questions that we've been looking at is just for maximum share allocations, can we improve on the factor 3/4? But other than that, I think a recent line of work is what we call the best of both worlds notion of fairness, which is about how can we get better results by incorporating randomness. For instance, let's take the classic example where we have just one good and we have two agents. Then whoever we give the good to would be happy and the other agent would get nothing. But let's say we do this randomly. We toss a coin, and if it's head, we give it to the first agent, and if it's tail, we give it to the second agent. Then that is a lot more fair, because now both agents have the same opportunity to get the item. So, but this randomness alone is not sufficient, because let's say we have a more general fair division instance, then again we can just randomly pick an agent and give all the goods to that agent. So this would be fair in the sense that each agent has the same opportunity, but this is a bad way of allocating goods, because there's a lot of disparity that one agent will get everything and the others will get nothing. So is it possible to get the best of both worlds? That can we randomize over fair allocate, approximately fair allocations? For instance, is it possible to get allocations that are to get a distribution over allocation such that each allocation in the support of that distribution is fair according to some notion of fairness that I've talked about so far. But the expected value, but if you look at the expected values of the agents, then would that be even more fair? So for instance, is it possible that, yeah, recently I think there was a result which said that there is a distribution over half MMS allocation such that the expected value of each agent's bundle is greater than or equal to their proportional share.
I see. Yeah, that's some form of ex post fairness. Okay.
Yeah.
Okay. Sounds good. Thanks. Yeah.
Yeah. Another area, set of problems that people have been working on are fair division when there are certain constraints. For instance, let's say we are allocating courses to students and we want to be fair to them. We don't want to give a lot of good courses to just a small number of students. Okay? But when it comes to allocating courses, there are constraints that if some courses have conflicting class times, then we cannot give those to, we cannot allocate two such courses to a single student. So there are additional constraints on what kind of allocations are allowed. Okay. Also, so in this talk, I've only talked about indivisible goods, but there's also an area where we consider divisible goods. For example, if you're dividing, let's say, a cake, then we can just cut the cake into as many pieces as we want. Okay. So let's say we're dividing land among people, then we would want to allocate contiguous chunks to people, not just, it'll be bad if we give like 1,000 different pieces from a lot of different places to one agent. That won't be.
This comes up in preventing gerrymandering also, for example. And one
Yeah.
other question, so so what about, other than additive valuations, for example, submodular valuations is of course something that is well studied. So what are some major questions over there?
I think all the questions that people have asked for submodular valuations, I guess most of them are also hold for, so most questions for additive valuations also hold for submodular valuations. For example, like do EFX allocations exist, approximate MMS allocations, etc.
Okay.
Yeah.
Okay.
And any known results for such submodular valuations?
Yeah, I think for submodular valuations, approximate MMS allocations exist. I don't remember the factor. I guess it's like maybe 1/3 or something. So it's worse than what we get for additive, and there are also, like, we know tighter bounds. So yeah. So yeah, work has been like MMS is the only thing that I'm familiar of in terms of submodular valuations. For like approximate EFX and all, I'm not really sure what has been done for submodular valuations.
Thank you.